340 days. That is how long the USS Gerald R. Ford spent at sea without coming home. Not 90 days. Not the standard 6-month rotation the Navy uses as its baseline for human endurance at sea. 340 consecutive days. The longest carrier deployment in modern American naval history. When the Ford finally turns toward Norfolk, you would expect a homecoming, flags on the pier, families waiting, a ship returning in triumph after proving that a $13 billion gamble on unproven technology could actually survive a real war. Instead, the moment that ship touches the pier, 5,000 sailors step off, and an army of shipyard workers steps on. Not to celebrate what the Ford survived, to operate on it. Because the Navy's most advanced warship, the ship that launched more combat sorties than any carrier in a generation, the ship that held the line in the Mediterranean and the Red Sea for nearly a full year, came home broken in ways that no peacetime test could have predicted, and no maintenance manual had a page for. Over the next 24 months, workers at Newport News Shipbuilding are going to cut open the flight deck, remove the most capable radar ever installed on a surface combatant, and tear through bulkheads to rewire the ship's nervous system from the inside out. This is Daily War Machine. We don't cover headlines, we cover what's underneath them. And what is underneath the Ford's homecoming is one of the most consequential maintenance periods in the history of American naval aviation. To understand what is about to happen to this ship, you have to understand what 340 days at combat tempo actually does to steel. The Ford was originally scheduled for a standard deployment rotation. It extended, then extended again. The Gaza conflict turned the Mediterranean into a sustained operational theater. The Red Sea added a second front. The ship that was supposed to come home became the ship that stayed. 5,000 human beings in a combat-ready state for nearly a year, not standing by, not on patrol, on. Every single day, the Ford's air wing executed combat air patrols over 2 separate theaters simultaneously. And every time that happens, the ship costs something it cannot get back. Here is the physics of what happens each time an FA-18 Super Hornet goes off the deck. The Electromagnetic Aircraft Launch System, EMALS, discharges a massive pulse of stored electrical energy in under 3 seconds. That pulse accelerates 50,000 pounds of aircraft and fuel and weapons from 0 to 165 miles per hour before the jet reaches the end of a 300-foot track. Every time that happens, the linear induction motors inside EMALS absorb enormous thermal and electrical stress. The energy storage capacitors cycle through a charge-discharge event that degrades their performance incrementally with each repetition. Then the jet comes back. The Advanced Arresting Gear, AAG, must physically absorb the kinetic energy of that same 50,000-pound aircraft arriving at 150 miles per hour and stopping in under 300 feet. That cycle, launch, recover, ran day and night for 340 consecutive days. The peacetime predictive models for component wear are built around standard deployment cycles. They account for sustained operations over months. They do not account for what happens when you run the machine at combat tempo for nearly a full year without stopping. By the time the Ford turned for home, the EMALS energy storage systems were showing wear profiles that the models said shouldn't appear for years. The AAG water twisters had been cycled far beyond their service curves. The cross-deck arresting wire pendants, the physical cables that catch the aircraft, had been replaced repeatedly. Each replacement a data point in a system being pushed past its design limits. And that was just the flight deck. Below it, the ship had a different problem entirely, one that no weapon system caused, one that 5,000 human beings created simply by being alive. The Ford's engineers made a weight-saving decision that seemed reasonable on paper. Instead of the heavy conventional sewage systems used on Nimitz-class carriers, systems built for exactly this kind of sustained use, they installed the Vacuum Collection, Holding, and Transfer System, VCHT. It works on the same principle as an aircraft toilet. Air pressure pulls waste through narrow pipes. Lightweight, efficient, modern. The problem is scale. A commercial-grade vacuum system serves 200 passengers on a flight that lasts hours. The Ford's VCHT serves 5,000 sailors every day for months at a time. Running a commercial-grade vacuum system at the biological load of a small American town is not what the system was designed to do. When the pipes clogged, and they clogged repeatedly, the Navy's only option was to run highly corrosive acid flushes through the system to break the blockages. Those acid flushes cleared the pipes. They also degraded the pipe walls from the inside out with each application. By the end of the deployment, multiple zones of the ship were dealing with failures that required creative solutions no engineer had written a procedure for. Then in March of 2026, a fire broke out in the ship's forward laundry facilities. The flames were contained, but the smoke and thermal damage that followed rendered adjacent berthing compartments uninhabitable. More than 600 sailors lost their sleeping quarters on a ship that was already running at the edge of human endurance. This is the cost that doesn't make the briefings. Not a weapon failure, not a combat casualty, a plumbing system that was never built for the war it was asked to fight. When a 100,000-ton nuclear-powered aircraft carrier enters a planned incremental availability, the scale of what happens next is difficult to fully picture. The Ford maneuvers into the dry dock at Newport News. Pumps begin removing millions of gallons of water around the hull. For the first time in years, the underwater body of the ship is exposed to open air. Workers erect miles of scaffolding along the exterior. Teams begin sandblasting the hull, removing the marine growth, the corrosion, the accumulated damage of a year in salt water at combat speed. A new coating goes on, not paint in the conventional sense. A corrosion barrier engineered to survive the next deployment and the one after that. Deep inside the engineering spaces, technicians begin the teardown of EMAL and AAG, pulling apart the high-voltage energy storage systems, inspecting the linear motors, replacing components that crossed their wear thresholds during 340 days of operations the system was not designed to sustain. The bronze propellers come out of the water for inspection and recertification. The advanced weapons elevators, the electromagnetic lifts that move munitions from deep storage to the flight deck, are recalibrated. The nuclear propulsion plant's secondary systems go through a full certification cycle. This alone, the propulsion work, the hull work, the system's recertification, would justify a significant maintenance period. But the work happening above the waterline is a different category entirely. The Ford was built with the dual-band radar, two systems integrated into one, the X-band AN-SPY-3 for low-altitude tracking and missile illumination, and the S-band AN-SPY-4 for volume search. Together, they give the Ford an electromagnetic picture of its surrounding airspace that no other surface combatant on Earth can match. It is, by any technical measure, the most capable radar ever installed on a ship. Over the next 24 months, the Navy is going to remove it, not upgrade it, not repair it. Remove it entirely. The reason is not performance. The reason is logistics. The dual-band radar is a one-of-one system. The USS Gerald R. Ford is the only ship on the planet that carries it. The Navy canceled it for every subsequent Ford-class carrier. Owning a weapon system that exists in exactly one hull means that when a component fails in combat, there is no warehouse with replacement parts. There is no supply chain. There is no sister ship you can cannibalize. To fix a broken DBR component, you have to reopen a manufacturing line to machine that one piece. In a sustained conflict, the kind the Navy is now planning for, a zero-commonality system is not an asset, it is a liability that cannot be repaired under fire. So the best radar in the fleet comes out. In its place goes the AN-SPY-6 Enterprise Air Surveillance Radar, the same system being installed on Arleigh Burke Flight 3 destroyers on new amphibious assault ships across the entire modern surface fleet. The SPY-6 covers one frequency band instead of two. That narrows the Ford's electromagnetic aperture. By that single metric, it is a downgrade. But the SPY-6 is built on gallium nitride semiconductor technology, more efficient, more reliable, and it exists in a supply chain that spans dozens of ships. If a system fails on the Ford in the Pacific, a replacement can be flown in from a supply ship that is already carrying the same module for the destroyers in the same strike group. Physics determines the range of a radar. Logistics determines whether it turns on at all. The Navy chose logistics. The most physically destructive phase of this maintenance period happens on the surface everyone can see, the flight deck. When the Ford was designed, the aircraft it was built around was the FA-18 Super Hornet. The flight deck, its coating, its blast deflectors, its surface geometry was optimized for the exhaust profile of the F-414 engine. The F-35C carries a different engine, the F-135. Inside the F-135's turbine section, temperatures reach 3,600 degrees Fahrenheit, hotter than the melting point of the turbine blades themselves, which survive only because engineers route cooling air through hundreds of microscopic internal channels in each individual blade. After that heat expands through the exhaust nozzle, the jet wash arriving at the flight deck still measures above 1,700 degrees. The non-skid coating that has protected Super Hornet flight decks for 30 years vaporizes under the F-35C at full military power. The jet blast deflectors, the steel shields that rise behind a launching aircraft to protect the deck crew, warp and buckle under the F-135's thermal load. To fix this, workers physically tear up the existing flight deck surface and apply thermal spray non-skid coating, a metallic alloy melted in a twin-wire electric arc and sprayed onto the steel to create a ceramic-grade thermal barrier. The old JBDs come out entirely. Active liquid-cooled replacements go in, with internal plumbing designed to dissipate the heat the F-135 produces on every launch. But the heat problem is only the surface problem. The F-35C is not just a fighter, it is an intelligence collection platform. Every sortie vacuums terabytes of classified electronic data that must be processed, stored, and transmitted inside a facility with specific physical and electromagnetic requirements. A sensitive compartmented information facility, a SIF. Building a SIF on a warship is not a software installation. Workers cut through solid armored bulkheads, temporarily compromising the structural integrity of the ship in order to weld in copper-shielded enclosures that block electromagnetic emissions in both directions. Independent ventilation systems go in. Acoustic baffling goes in. Miles of air-gapped fiber optic cable get routed through spaces that were never designed to carry them, connecting the SIF to the Odin system, the operational data integrated network that will make the Ford the intelligence hub of its strike group. When the first F-35C squadron finally lands on this deck, the Ford will no longer function as a standalone strike platform. Through the F-35C's sensor fusion and the Naval Integrated Fire Control architecture, the carrier becomes the targeting brain of an entire networked fleet. Aegis destroyers will be able to fire SM-6 interceptors at targets they cannot see, because the Ford's F-35Cs will see them and pass the firing solution across an encrypted network at the speed of data. 24 months of surgery to unlock that. Step back from the individual systems and look at what this maintenance period actually represents. The Ford went to sea with a radar that had no supply chain. It went to sea with a plumbing system that was not built for the biological load of a full crew at combat tempo. It went to sea with a flight deck optimized for an aircraft a generation behind the one it now needs to carry. And it operated that way for 340 days across 2 active theaters, launching strike missions, maintaining combat air patrol, deterring escalation in both the Mediterranean and the Red Sea. None of those systems failed catastrophically. The EMALS launched. The AAG recovered. The nuclear reactors ran without fault. The ship did its job. But the Ford was never a finished product. It was a test article forced into operational service because the threat environment did not wait for the engineering to mature. The ship that is entering dry dock now is not the ship the Navy planned to build. It is the ship the Navy had to build to prove that the underlying architecture, the electromagnetic launch, the massive nuclear power plant, the distributed weapons elevator system, could survive real warfare. It proved it. Now comes the standardization. The USS John F. Kennedy, CVN-79, is completing sea trials right now. It was built from day one with the Spy-6 radar, a thermally hardened flight deck, and life support systems designed around the lessons the Ford paid for with broken pipes and acid flushes. Every failure the Ford absorbed, every system that failed under sustained combat tempo, every design assumption that collided with operational reality, it all goes into Kennedy's steel before that ship ever touches salt water. The Ford is not being repaired. It is being standardized, rebuilt to match the fleet it created. There is a particular weight to being first. Not the glory of it, the cost. The first ship of a new class carries every unproven assumption, every untested integration, every engineering decision that looked correct on paper, and reveals its flaws only when 5,000 people live inside it for nearly a year at war. The Ford carried all of it. A plumbing system that failed under the weight of the crew, a radar unique on Earth with no backup and no supply chain, a flight deck built for a jet that could not yet land on it, and a launch system that had never run at this tempo for this long in a real war. It ran anyway. 340 days, 2 theaters, the longest carrier deployment in modern history. And when it comes home, it does not get a rest. It gets a surgery that will last longer than the deployment did. That is the price of being the future. Not the ribbon cutting, not the commissioning ceremony, not the first deployment. The dry dock, the scaffolding, the workers cutting into steel that a year ago was in the middle of a war. The Ford absorbed the cost of inventing the 21st century carrier so that every ship that follows gets to start where the Ford finishes. Kennedy gets the hardened deck. The ships after Kennedy get the data from that deck. The first of a class always pays the highest price. That is not a failure. That is the function. This is Daily War Machine. If the Ford earned its scars, drop steel in the comments. Subscribe. We cover what the headlines skip.